All right, in section 1.3, we are going to start looking at a review of trigonometry. We're going to kind of look at the big parts of trig that we will use in Calc a lot. We're going to do this in two parts because there's a lot of trig that we will eventually use, so we're going to try to take our time, do a little bit in each part. So if you recall what a trig ratio is, a trig ratio by definition is going to be the ratio of two sides in a right triangle. And then, of course, there are lots and lots and lots of applications that we can do with these ratios. But in essence, this is where it all starts. It all starts with the ratios in a right triangle. So if you look at the right triangle we have here, I have this generic triangle. And so if you recall that if you have this triangle, we have our right angle. So if I pick an angle theta, I'm going to pick this one in this corner with the angle B. Then we have an opposite side. We have a hypotenuse, which is always the side across from the 90. Then the other side we call adjacent, which is just next to, so it's the side next to it. So from these, we will assign the different ratios of all these sides. So for example, we might say take this side and divide it by this side. So we're going to take the opposite divided by the adjacent. And the idea is in any triangle that has these angles. So if I have another really little triangle that has theta and a right angle in it as well, the ratio of this side and this side will be the same as the ratio of the opposite and the adjacent in the bigger triangle. It's a concept of similarity, but we always have the same ratios in any triangle that has the same angles. So if you recall, we have some different ratios. We have our basic ones. We have our SOHCAHTOA ones. Sine is the opposite over hypotenuse. Cosine is the adjacent over hypotenuse. And tangent is the opposite over adjacent. So those are our basic ones, and you can just take the ratio of those two sides in a triangle. And it's always the same for any right triangle that has those angles. The last three, if you recall, are reciprocal. So cosecant is the reciprocal of sine. So sine is opposite over hypotenuse. So cosecant is hypotenuse over opposite. Same thing for secant and cosine. Secant is hypotenuse over adjacent, while cosine is adjacent over hypotenuse. And then finally, we have tangent and cotangent. Those are also reciprocals because one is opposite over adjacent, one is adjacent over opposite. Now, a majority of the time, we can get away with the first three, but there will be times and problems that we will see with the second three, and we either have to convert them to the first three or kind of deal with them how they are. So let's look for this example where we're going to find the 6 trig ratios for the angle theta in the triangle below. So the first thing I want to do is I want to define our sides. So the one across from the 90, remember, is always the hypotenuse. The one across from the angle we're given, so in this case this is theta, this is going to be the opposite side because it's across from it. And then this, of course, is the adjacent because that's the leftover side. Now, unfortunately, in this case, we do not know what the adjacent side is. So we'll call it x. But of course, we know in any right triangle, the three sides of a right triangle are always related with Pythagorean theorem. So x squared plus 3 radical 6 squared equals 9 squared. So I can find x from this. So we get x squared, 3 squared is 9, radical 6 squared is 6, equals 81. So this is 54, so I'll subtract 54 from both sides. So that's going to give me 27. And then I'll take the square root. So x equals the square root of 27, or if we simplify it, that is going to be 3 radical 3. And remember, when I'm doing radical 27, there's lots of ways to simplify this. I know a perfect square that goes into it is 9, so I can go 9 and 3, and that becomes 3 radical 3. That's one way to do it. The other way to do it is you could say, all right, well, 27 is 3 times 3 times 3. It's 9 times 3 and then 3 times 3. And so you have one group of 3s, so that goes on the outside, and one not matched up 3 that stays on the inside. So however you simplify radicals is okay by me. So now we have all the sides, so now we can find our ratios. So we have the sine of theta is going to equal the opposite over hypotenuse. So that's 3 radical 6 over 9, which is radical 6 over 3. The cosine of theta is adjacent over hypotenuse. So that's going to be 3 radical 3 over 9, or radical 3 over 3. And the tangent of theta is opposite over adjacent. So that's going to be 3 radical 6 over 3 radical 3. So you have two radicals divided, which you can just divide the numbers inside, so you get radical 2. Now for our other three, cosecant, remember, is the flip of sine. So that's 3 over radical 6. You can rationalize this. If you remember what rationalize mean, it means get rid of the radical on the bottom. That would be 3 radical 6 over 6, which would then simplify to radical 6 over 2. But you will actually see in calculus, it's sometimes better not to rationalize, and there will be functions and things that we don't rationalize, because to do certain things with it, we'll have to keep that radical on the bottom. But it's really up to you. Secant is going to be the flip of that, so 3 over radical 3, or if you rationalize, that's just radical 3. And the cotangent is going to be the flip of that. It's 1 over radical 2, which rationalizes radical 2 over 2. So next thing we're going to look at is the difference between radian and degree measure. Now remember, these are both ways to measure angle. The radian measure, radians is always going to take the ratio of the arc length to the radius. Now in calculus, we almost always want to use radians, so if we have something in degrees, we want to switch it. So we have the conversion formulas that if you have something in degrees and you want to turn it to radians, we could just multiply that by pi over 180. Now, not done as much in Calc as going from radians to degrees, but if you wanted to, you just multiply the angle, which is in radians, by 180 over pi. So both formulas work. It's just basically the reciprocal of one another depending on which way you're going. So if we look at these, this first angle is in degrees. So let's say I wanted to find the radian measure of that. Well, what I'll do is I would simply multiply this by pi over 180. And so the degrees cancel. So really what we have is we have 120 over 180, which the zeros will cancel. So 12 over 18 both divide by 6, so we get 2/3 pi. Remember, your radian measure should always have a pi in it. That's just typically how we break it apart. So the second one is pi over 5. So if I want to turn that into degrees, I'll do 180 over pi. So the pi's will cancel. So we're just left with 180 divided by 5, which is 36 degrees. Now again, most of the time we'll be going from degrees to radians because we really like radians. Most of the formulas and functions that we will define in calculus will really specify that your angle has to be in radians. All right, another thing we'll have to do quite a bit is we'll have to find the value of some trigonometric functions at certain angles. So this would be if I knew what theta was, let's say theta was 30, then what is the sine of 30 degrees? And what is the cosine of 60 degrees? What is the tangent of 15 degrees? So these are all the special ones that we talked about in pre-calc that we can use using reference angles or using the unit circle. So here is our unit circle. If you remember unit circle will tell us some of the special angles, and then every point on this unit circle will tell us the cosine and the sine of that. So the sine of an angle is the y value, and the cosine is the x value. And then remember, you can always get one of these angles on here. If it's not on here, you can add and subtract 360 to get an angle on here. If that still doesn't work, then it's probably not one that we can find exactly. So if we look at this first one, it says, what's the sine of 225? Well, here's 225 right here. So here's the x, here's the y. And remember, the sine is the... So the second coordinate is just simply negative radical 2 over 2. So the sine of 225 is negative radical 2 over 2. Now the next one says, what is the cosine of 15 pi over 4? Well, unfortunately, I don't see 15 pi over 4 on here. So we can do a couple things. So the first thing I'm going to do is I'm going to convert it to degrees because I like degrees better when I'm trying to find things on the unit circle. So these pi's will cancel. 180 divided by 4 is 45. So now we'll just figure out what is 15 times 45. Now it's going to give me 675. So the cosine of 15 pi over 4 is the same as the cosine of 675. Well, again, 675 is still not on my unit circle, but what I can do now is I can take 675 and I can subtract 360. So when I do that, I'll get 5, 1, 315. Hey, and 315 is on our unit circle. So now we're going to use this point. Well, since I want the cosine is the x-coordinate. So our cosine of 675, or 15 pi over 4, is going to be radical 2 over 2. So if you don't have a copy of the unit circle, you could certainly use this one, or print out one of the bigger ones if you don't have the one from pre-calc. That'd be pretty helpful. All right. Now the next one says tangent of negative 30. Well, again, negative 30 is not on there, but it is in degrees. So what I'm going to do is I'm not going to subtract 360. That would make it more negative. I'm going to add 360. So negative 30 plus 360 is 330. So the tangent of negative 30 is the same as the tangent of 330. So 330 is a point on here. It's this guy here. But tangent is not one of our 2 points. The points directly give you cosine and sine. But tangent is the sine divided by cosine, or the y divided by x. So for this case, I'm going to take its y over its x to get its tangent value. So that's minus 1/2 over radical 3 over 2. Now the nice thing about this is the 2's will cancel. And so I just end up with negative 1 over radical 3 as my tangent value. If you did want to rationalize that, that's negative radical 3 over 3. That works too. Okay, the last one we have here is the secant of 3 pi over 2. Well, 3 pi over 2 is on my unit circle, so that's good. We just don't have secant. Well, secant, remember, is the flip of cosine, so it is the flip of the x-coordinate. So the x-coordinate here is 0, so I'm going to take 1 over 0. Well, unfortunately, we can't divide by 0, so this is going to be undefined. And for some of these quadrant angles, 90, 180, 270, it is very common for secant, cosecant, and tangent or cotangent or tangent to be undefined. So don't be kind of worried if you get an undefined value. All right, the last thing we're going to look at is some trig identities. Now, if you remember trig identities are going to be expressions that are the same. So we have lots and lots and lots of trig identities, and it would be a good idea to kind of commit these to memory, because if you remember from last year, we would take them and switch them and convert them. So we're going to do similar stuff this year. If we see a difficulty expression and we don't like it, we might try to use the trig identities to make it a little simpler for us. Coordinate. So here's just kind of a collection of some of the identities I think are the most important. So you have the reciprocal identities, where you're just flipping them over. And quite honestly, I would say that we use these more than the top ones, because I never really want to change sine and cosine to other things, but I definitely want to change secant and cosecant, things like that. The quotient identities, tangent is sine over cosine, cotangent is cosine over sine, very, very important. And then we have our Pythagorean identities. So we have the sine squared plus cosine squared equal 1. And if you recall, we talked about rewrites in pre-calc, and here are those rewrites where you can rewrite that basic Pythagorean identity 2 other ways. So you can get the cosine squared by itself or the sine squared by itself, depending on what you're looking at. Even odd identities are good. We don't use those a ton. We have the angle addition and subtraction formulas, so those are good. We won't use those a ton, but we use those in a couple proofs when we're proving some derivatives and such. Same thing for double angle and power reducing. These are all good ones that we can use, but we don't use these a ton. So I put them on here. We might refer back to these. So if you have this page, I'm pretty confident this will be an exhaustive list of everything we need. So if you have these, when we start looking at those, you'll know what to look for. So what I want to do is let's look at a couple examples where you can simplify a couple expressions using these identities. So this says simplify the following. So I'm going to have all those identities in front of me, and I'll just kind of go through the process of what I would think. So I see tan squared plus 1 here. So I look at my identity sheet, and on my identity sheet, I know that there is tan squared plus 1 actually equals secant squared x. That's a direct identity. Then on the bottom, it has 1 plus cotangent squared. I know that is cosecant squared. Now, anytime I see the squared, I'm usually looking at that block that has the Pythagorean identities because those can convert pretty easily. Now, I know that secant is 1 over cosine, so secant squared is just simply 1 over cosine squared. And cosecant is 1 over sine, so cosecant squared is 1 over sine squared x. Now, this is very, very common where you'll get a fraction over a fraction. And then what we like to do is we will multiply by the reciprocal. So this is 1 over cosine x times sine squared x over 1. So that is going to give me simply sine squared x over cosine squared x. But if you remember from our identities, sine divided by cosine was an identity we had. Sine divided by cosine was tangent. So sine squared divided by cosine squared is tangent squared. All right. So let's look at the next one. Again, we have some squares. So when I have squares, I'm thinking, all right, I'm probably going to be dealing with those Pythagorean identities. Now, I generally, if I have a single thing like cosine squared, I typically don't want to change that. But this 1 minus cosine squared, if I look at my rewrites, 1 minus cosine squared is the same as sine squared. So I can rewrite this as cosine squared over sine squared. We always like to take things that are binomials, 1 or 2 things added together or subtracted, and make it one thing. That makes our life a lot easier. Cosine over sine is going to be cotangent squared. Because cosine over sine is cotangent. They both have a square on it, so we'll say it's cotangent squared. All right, the last one, this is kind of a tricky one because it's 2 things added together. I don't have anything for 1 minus sine. I have something for 1 minus sine squared. So I'm really kind of stuck here. But the kind of key in this one is I have the addition sign. So whenever I'm adding, I can add 2 fractions together if I get common denominators. Well, since I have 1 plus sign and 1 minus sign here, my common denominator is simply going to be 1 plus sign, 1 minus sign. And then whatever I'm missing, I'm just going to add. So the first one I had cosine. The bottom is 1 plus sign, so I'm missing 1 minus sign. So I'll put that in. Plus, I have cosine here. So I had 1 minus sign, so for this one I need to add 1 plus sign x. So that's just adding the fractions with our common denominator. Now we have a bunch of simplifying to do. We can distribute the cosine here and here. So that's going to give me cosine x minus cosine x sine x. And then I'm going to get plus cosine x plus cosine x sine x. And on the bottom, I will FOIL. So I'll get 1. And then I'll get minus sine x. And then I'll get plus sine x. And then I'll get minus sine squared x. Now, the good news is you can see that lots of stuff cancels. This cancels with this because they're both negative and positive cosine sine, and then our sines go away. So now let's see what we end up with. Well, we end up with 2 cosine x on the top because I just have 2 of the same terms added. And on the bottom, I have 1 minus sine squared x. But 1 minus sine squared x is cosine squared x. That's one of our rewrites that it should be under your Pythagorean identities. So we get 2 cosine x over cosine squared x. So then we can eliminate one of the cosines. So we get 2 over cosine x. That would be fine. Or if you wanted to go further, since 1 over cosine is secant, I could actually finish this and write it as 2 secant x. I think I kind of like 2 over cosine better. I guess it just depends on what kind of thing we're doing in calculus. But both are actually the same identity, just written different ways. So this is kind of your first part of your trig review. In the second part, we'll talk about the graphs of the trig functions and our trig equations, which are probably the most important thing we will do kind of going forward. But if you have questions on the first part of this, obviously let me know.